Hello everyone. Today we'll start with the final lecture on pre-stressed concrete and the third method, that is nothing but the load balancing method. So in the previous lectures we have already seen both the methods, that is your stress method and the pressure line method. So in this lecture we will do load balancing method. So what is load balancing method? Let us see. If the beam is so designed that the upward force transmitted by the tendons exactly neutralizes the externally applied load, then the method is called load balancing method. So I hope it is clear by this statement that in this method the objective is to design the beam in such a way that the upward force transmitted by the tendon exactly neutralizes the externally applied load. Okay, so this is the concept of load balancing method. So depending upon the shape of the tendons, various types of reactions act on the concrete member. For example, a straight cable does not induce any reactions except at the ends. That means if a cable is straight, so you will have reactions only at the ends. A curved cable will result in uniformly distributed load. So if you have a curved cable, so the upward pressure which it will induce in the member will be your uniformly distributed load. And if you have a bent tendon, so it will induce a concentrated upward load. So the load balancing concept is useful in selecting the tendon profile. So this method is basically used to actually select a suitable tendon profile for the section. So now let us just go through the equations involved in this. So net downward force for different tendon profile. So basically we are going to find out the net downward force for different tendon profile. So net downward force is given by downward force minus upward force, where downward force is nothing, the force due to the imposed load, and upward force is due to the stresses in the tendon. So let us see the first, that is beam with the bent tendon. So this is a longitudinal section of a beam in which you can see a bent tendon with eccentricity E at the center and pre-stressing force P, and theta is the inclination of the tendon with the horizontal, and the span is L. So here upward force is given by 2P into tan theta, and tan theta, as you can see I have mentioned, it is E upon L by 2. So tan theta is opposite upon adjacent. So upward force is given by 4PE by L, and the downward force is W. So by load balancing method, if you equate upward force with the downward force, you will get the equation in terms of W, which is given by 4PE by L. So you just have to remember this value of W, which is 4PE by L, which we are going to use in the numericals. Now the second case is beam with curved tendon. So again you can see a longitudinal section of a beam with UDLW, and the tendon profile is curved with an eccentricity E at the center. So the upward force Px is given by WL square by 8E. So therefore WC is the upward force of the tendon profile. It is given by 8PE upon L square. So these two things you have to remember while solving the numericals. So the resultant stress in the load balancing method is given by the equation F top is P by A plus M by ZT. So there is a slight change in this method when you find out your resultant stress. So where M is nothing but mg, that is dead load bending moment, plus live load bending moment, and this mq is nothing but the net live load. So this net live load is given by net downward load into L square upon 8. So this you have to remember. Similarly, F bottom is given by P by A minus M by ZB. So now with the help of this theory, and we can solve the numericals. So let us go to the first problem of this method. Okay, so the question is, the figure shows a PSC beam provided with a tendon having a parabolic profile. If the external load on the beam is 35 kN per meter on the whole span, find the extreme stresses at the midspan section by load balancing method. The tendon carries a pre-stressing force of 1000 kN. Okay, so what basically is asked in the question is to find out the extreme fiber stresses with the help of load balancing method. So I have drawn the cross section and the longitudinal section with the dimensions. Your live load is 35, pre-stressing force is 1000, span is 6 meters, and eccentricity is 100 mm at the center, and your profile is parabolic. So we have to find out f top and f bottom by load balancing method. So the first step we'll find out is the section properties, area, your moment of inertia, and z, which is nothing but I by y. Now the second step, coming to the second step, to find out the loads and bending moments. So this is important. So first we'll find out the self weight of the beam, which is given by section dimensions into the density, which comes out to be 6. So now we have to find out the net downward load, which is given by downward load minus upward load. So first upward load, downward load is already given in the question. What we have to find is we have to find out the upward load. So upward load transmitted by the tendon WC, which we have seen in the theory part, that is WC is nothing but 8PL 8PE upon L square. So with the help of that, we are finding out the upward load transmitted by the tendon. WC is equal to 8 into P into E upon L square. So we got it as 22.22 kilonewton per meter, and downward load is 35 kilonewton. Here you can see it is given in the question. So your W net downward load will become 35 minus downward load minus upward load, so which comes out to be 12.78. so now you have to find out bending moment due to dead load and also the net downward load. So this is important, net downward load. So mg is this and mq is w net into L square upon 8, where w net is 12.78. so therefore total bending moment becomes mg plus mq net. So therefore your resultant stress is given by the equation P by A plus M by Z, where M is, remember, mg plus mq net. So P by A plus M by Z will give you 7.68. And similarly, F bottom is given by P by A minus M by Z. So this is how you are going to find out your resultant stress with the help of load balancing method. Okay, so now we will see the next problem, which is very important, in which you will see all the methods in one problem. So let us see what is that problem. So a PSC beam 500 by 800 mm deep is simply supported on span of 10 meters. It is pre-stressed with a linearly bent tendon with zero eccentricity at the ends and an eccentricity of 200 mm below the axis at the midspan. The beam carries a concentrated load of 150 kN at the center besides its self weight. Compute the extreme fiber stresses at the midspan using the stress concept, the strength concept, and the load balancing concept. Take pre-stressing force P equal to 180 kN. So now this is a very interesting question in which you have been asked to find out the stresses with the help of all the three methods, that is your stress concept, the strength concept, and load balancing concept. So first let us draw the figure. What is given in the question, the cross section is 500 by 800 and it is a bent tendon with zero eccentricity at the supports and an eccentricity of 200 mm at the midspan. The span is 10 meters and your load is, the point load is 150 kilonewton. Okay, so we'll start with the solution. The first step is we'll solve by stress concept. So first we'll find out the section properties, that is area, moment of inertia, and section modulus. So this we have already seen. In the second step we'll find out the loads and bending moment. So dead load of the beam is given by sectional dimension into the density, which comes out to be 10, and live load of the beam is 150 kilonewton. So your dead load bending moment will be WL square by 8 since it is a UDL, but remember your live load bending moment, since it is a point load, will become WL by 4, where W is 150 kilonewton given in the question. So you got your mg and mq. So the resultant stress will be given by F top is P by A minus PE by Z plus mg by Z plus mq by Z. So this comes out to be 9.16 Newton per mm square. Similarly, your F bottom is given by P by A plus PE by Z minus M by Z, and it comes out to be minus 8.26. So we got the resultant stresses with the help of the first concept, that is your stress concept. Now we will go for the second concept, that is strength concept or the pressure line method. So in this, the resultant stress, remember the resultant stress is given by P by A plus or minus PE dash by Z, where E dash is nothing but A minus E. So in the last numerical we had seen how to find out or plot the pressure line. So here we are actually going to find out the resultant stresses with the help of the pressure line method. So your E dash is nothing but A by E, where A is equal to M by P. So first we will find out the shift of the pressure line, that is A at the center, that is M by P. M is given by 500 into 10 raised to 6, your moment, that is the total moment, that is mg plus mq, and P is 180. So you got the value of A. So now to find out E dash is given by A minus E. So E is given the question as 200. So you got the value of E dash. So now F top is given by P by A plus PE dash by Z, where E dash you have just calculated. So this gives your F top as 9.16 Newton per mm square. Similarly, your F bottom is given by P by A minus P into E dash by Z. So remember, in this the formula is P into E dash, where E dash is A minus E. So F bottom you got it as 8.26 minus 8.26. So now you can see from the first method also we got F top as 9.16 and F bottom as minus 8.26. Okay, so now we will go for the third method, that is the load balancing method. So again in this we will find out the section properties which we have already done, then loads and bending moments. So dead load of the beam is given by 10 kilonewton per meter Wg, and net downward load W net is downward load minus upward load. So upward load is given by, we have done in the theory, 4 into P into E upon L. So W net is downward load minus upward load. So 150 minus 14.4 becomes 135.6. So moment due to dead load mg is remains the same, WL square by 8. Now moment due to dead load mq is WL by 4, where W is W net. So it comes out to be 339 kilonewton meter. So total bending moment M is mg plus mq net. So now the resultant stress for the load balancing method is given by P by A plus M by Z, where M is the total mg plus mq net we have seen in the first problem. So F top we got it as 9.16. Similarly, F bottom is P by A minus M by Z. So it is minus 8.26. So now you can see from all the three methods, the resultant stress we are getting is the same. So we can find out the resultant stress with either of these methods, whichever is suitable. So you can see here from the first method it is 9.16 and 8.26. The second method same, and the third method. So now I am just drawing the stress distribution diagram for this. So this is the cross section, and the resultant stress is at the top it is compression, at the bottom it is tension. So this is how we are going to solve the problem when it is asked to solve with the help of all the three concepts. So basically we have done all the topics which is given in the syllabus for the last module, that is pre-stressed concrete. And if you do all these lectures, if you go through these lectures, you'll definitely be able to solve any problem in the exam. So I hope you understood the lecture and all the lectures which I have uploaded before. So thank you.